All right, welcome back. So let's just call this, I'm moving into section 5.3, where the title is Riemann sums and the definite and definite integrals. But I introduced this kind of in the last video. I talked about how this is, and I didn't use the word Riemann sum, but when you're adding up the heights and the widths of the rectangles, the heights and the widths of n rectangles, you're estimating the area under a curve. Of course, when you take the limit and let the number of rectangles goes to infinity, now you have the exact area under the curve, and what that is a definite integral. So when you take, without this, it's an estimate of the area under the curve. The more rectangles, the better estimate. And when you do the limit as n goes to infinity, it is the area under the curve. And you can do a definite integral to get that. And I taught you how to do that, which is technically up in 5.4. But it's the area under the curve, and you know, here's an abstract sum function from A to B, the area under a curve, we kind of call it. Technically, it's the area under a curve down to the x-axis. It's not infinite area under the curve. It stops at the x-axis. So in 5.3, the homework is just a little funny because, again, they haven't taught you how to do this. I taught you how to do this by jumping ahead to 5.4. But in 5.3, they have these kind of questions. Here's a function, y equals 6x minus x squared. They want you to set up an integral to find that area. Set up an integral to find that area. You know, I didn't do this on purpose. You might need to know your a and b. And in order to find a and b, I'm looking for these x-intercepts, I guess. And so maybe I need to do a little algebra here, trying to find the x-intercepts. I'll set this equal to 0. I'll factor out an x. And x is 0, and x is 6. So it touches here at 0, and it touches here at 6. Okay, cool. That's what I needed. And now I think I can set up an integral to find this area. I think the integral would be a definite integral from 0 to 6. That's how you talk. It's a left bound and a right bound of integration. These are called the bounds of integration. The left bound and the right bound from 0 to 6. And who are we integrating? We're integrating this function. The function that's in the picture is who you're integrating. And so, yeah, that was easy. And a lot of 5.3 questions are trying to make you see, go from the picture to the integral, or go from the integral to the picture of the shaded area. So a definite integral represents an area under a curve, or the area under the curve represents the definite integral. And you kind of go back and forth, and again, they hadn't really taught you how to do this. So a lot of you're not doing the integral. Let's just do it. We know from section 5.4 that you find the antiderivative. You actually integrate. Let's see, power rule, x squared divided by 2. I think that would be 3x squared. X cubed divided by 3 minus x cubed divided by 3. I'm going to evaluate. I don't put a plus c on a definite integral. I'm going to evaluate from 0 to 6. That means plug in the 6. I'm going to move up here a little bit. 3 times 6 squared minus 6 cubed over 3. That's me plugging in a 6. Minus, you're supposed to plug in a 0. In this case, I get a 0 and a 0. Be careful, you don't always get zeros there, but in that case, there's nothing there. So just got to do some math. 36 times 3 is 108 minus, oh my goodness, I think that's 72. I think that's 72, that's 36, yeah, I think that's 72. When I subtract that, that's 36. So, what's this area? 36. You mean it's kind of close to 36? It's kind of, you know, it's estimate to be? No, dude, that is the exact area. The exact area under the curve is 36. I mean, this is amazing, man. Prior to this, what could you do? You could do the area of a rectangle. You could do the area of a triangle. You could do the area of a trapezoid. I mean, you had formulas from geometry. You could do the area of a circle. But, dude, we're doing the area of parabolas. We can do the area of any crazy shape as long as we can integrate it. So we get the exact area under the curve. It's an amazing, amazing revelation in calculus. You are powerful. You are powerful.